Alright, I got a new project going on. Sorry for the string. So this is about the flying shear model. So we have the master over here, which contain two marker. This is to simulate the conveyor belt, and this is to simulate the object that we need to sync. And up here we have a servo. Oh, sorry, the servo is on, so we cannot move it. But the proposal is that we have to move the green marker to match the movement of the yellow and the red marker. And we have the entire sync zone over here. And the way we hit the end is how I'm going to measure the timing difference between the two systems, because I want to have some kind of benchmark to see how well I'm singing it. So this project has been done like a lot on the internet, but I couldn't manage to find any reproducible resource readily for me. So you know what, let's make it the first one to be readily available. Okay, so that is the main idea, and this is a very common project for engineering major. Let me check. Okay, so this is another project. Let me just check it for you. Let's skip it a bit. So what we are working for is applicable for systems such as a cutter. In this case, instead of having to stop the conveyor belt, we can just move the cut head along. Let me right here. Yeah, this is the cut head. Yeah, the cut head sync with the cut position and just cut along the movement of the belt. The belt doesn't need to stop and start multiple times and doesn't affect the production. So that is pretty neat, right? This is actually used a lot. The video is actually from Mitsubishi themselves, and this is a pretty nice demonstration of the system, as you can see right here. So they have the white marker, the white marker, and the tool head, red tool head, have to synchronize with that. They use a ball screw actuator while I'm using the belt. I think both of them are fine. Just the problem here is how to sync it, and what is the performance of the syncing action, like how fast can you move the tool head back to the mark without overshooting the destination, and how quickly can you accelerate to catch up to the marker without overshooting the marker. So it's a problem about positional control. And this is another example of the flying shear. So this is a flying saw. Saw will move. The position of the saw will move to catch up, and then quickly move back to the start position in order to reset the cut. And because if the movement between the saw and the pipe in this case is not matched, the saw blade is definitely going to break. I remember these things are usually made of stone or something like that. So yeah, they are definitely gonna break if there are any lateral movement. This is a much nicer demonstration from Mitsubishi Electric themselves. I believe the the diagram here explains the situation pretty well. So it depicts the position, the speed, and a similar situation for the belt. So we can see that the position of the cut head move linearly to match the linear movement speed of the conveyor, and then if rapidly move in the opposite Yeah, and then it rapidly moves in the opposite direction in order to reset the cut. So that is the problem we are dealing with today. Yeah, another one of them is the stamping. There are a lot of pre-made systems that handle this kind of thing. This is like a stamping actuator. And yeah, like I have said before, this is very it has been done a lot but it's still used in a lot of theses because it demonstrates the need for understanding of such a system. That I think in the real life they already made some system that are pre-configured for you. So if you buy all the components from that vendor, you don't even need to program your own controller. You just need to set your parameters, like how fast should it move, and their own program will take care of all the positioning. So a pretty nice solution for like factories. The problem is that you might get into vendor lock-in and you know what happened with vendor lock-in, right? So move on, master slave servo. Okay, I think we are good with that. Now about the system we are moving. Okay, so for the conveyor belt I have a Mitsubishi motors. Let's turn it on real quick. So this baby is it's actually due to that's actually not an error, but due to the loose contacts it can trigger the error. So that error that you just saw it flashing is due to the poor contacts of these connectors. These are very old hardware, but for the sake of demonstration they do the work just fine. Yeah, so just don't touch them, make sure you wire them correctly. So for the conveyor I use a induction motor paired with a Mitsubishi A800 variable frequency drive, and it is not in the correct mode right now. Let me fix that. 79.2, so I'm just configure it. Oh, I should have set it to 79.1 first, because right now it is in network mode, which is not what we wanted. I want to control it externally using just the controller over here. So this is a very old controller, FX1S30MT, an old controller from Mitsubishi. I think we got it now. Okay, let's give it a bit of a demonstration, shall we? So go to online. Let's check the connection, shall we? Okay. Make sure this thing is on the running state, so we have a switch over here. And we can go into online, monitor, and monitor mode. So output Y1 is the command we are using. So let's go into device test, setup. What is default, right? Default is our frequency. Let's give it something like 2000. Oh, I have done the scaling in a different paper, 32-bit integer. This is not Y1, this is M3. Just a setup. Okay, we set the frequency. This is not 2000 Hertz, just to be clear. This is 2000 pulse from the programmable logic controller to the variable frequency drive. So when I hit this button, it should run the motor. I have the mouse right here. You have to spend a bit of a time to recalibrate the belt tension. It is moving, but it's a bit slow, so how about we change the, let's give it something like 5,000. You probably can already hear it moving a bit too slow. Let's bump it up, right? 10,000. Yeah, what you are hearing, the bumping sound, is actually the belt tension problem. So it is now moving at a maximum speed I configure for it, which is 30 Hertz. The max speed of the motor is actually the more nominal speed, the rated speed, I'm sorry, of the induction motor is 50, but my servo is definitely not going to be able to catch up with that kind of speed when trying to synchronize the position of the two marker. Right now I think the position is actually backwards, so I have to fix that later. Yeah, so I got it running. A bit noisy. I don't know if you can hear it very well. I can easily do this. Of course, I'm not going to do all kind of the manual bit manipulation like that. So that is the servo thing, right? Now, I'm sorry, the induction motor. Now we go for the servo, which is controlled by the Y1 command. How about we check it? D2 is the frequency. So let's make it pretty fast, but not that fast. Shall we? 32-bit integer. Is it D2 or D0? Yeah. I'm wearing the camera, so yeah. 10,000 Hertz. This thing can go up to 100,000, so I'm not going to be, don't have to worry about that. Boom. D0, I think D0 is the number of poles. Let's give it 5,000. And when I set the M0, it will execute this command. Gonna hover on the button right here, and we can watch the action on the servo. Oh, I think you guys missed it, so I'm just gonna do it again. Seven oh 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 oh. Because after it complete this command, the flag M802 now will reset the bit. So this is basically just a way for me to check the command on how to control the servo. Let's go again. Yeah, so with 70,000 poles, it's going to go around a lot. 70,000 is the amount of poles we are going to send, and 10,000 is the frequency of poles we are sending in. So let's go for another case. Let's slow down the frequency. So let's speed it up, right? 100,000. Yeah. Okay, set it there. And when we do this, it's going to try to send 70,000 poles with the frequency of 100,000 Hertz or 100 kilohertz. So it should look something like this. I think my mouse missed the action. Oh yeah, I should change the number because the command has actually completed is action. It is being reset. Let's change this thing to 80. Sorry. Yeah, 80,000. Set it. Now get ready for some rabbit movement. We are basically 10 times the speed. I don't think I catch that. So let's dial it back a little bit, shall we? D2 for the sake of demonstration. I think 10,000 is a nice number. And for D0, let's give it something like 5,000. So it should give you something to, Y3 is the directional speed, which I can turn on or off up there. So let's do it now. So let's turn on M2. Okay, we'll force that on. Y3 is on, so it should turn the opposite way now. Go back to M0, and when we force this thing on, it should go in the opposite direction. Okay, no, that actually looks like intended. Okay, I already got those part down: power supply, movement, input, output, sensor, and the nice part is about the encoder over there. I'm going to turn the power off for now, so I can move the tool, the marker myself. You see, on this thing there is a rotary encoder which tell me how fast the induction motor is moving and the direction of the induction motor. And we have to use some high speed counter on the controller to do that, but I'm not going to the details. The problem I am having right now is the methodology on how to control it. So let's take an example. My plan is to home both of these into this induction sensor. A bit about the induction sensor for context. There's a nail with a 3D printed surrounding it, and when the sensor detects metals, it will light up and send a signal to the controller. Alright, so my plan is to home both of them. The servo have an encoder, so my plan is to rotate it back. I can actually control how much it goes back, so I'm gonna try to set it back here. Same thing for the induction motor. So I have also calculated from this point, from the point in which the sensor detect the marker, it will count based on the rotary encoder how many poles has passed before it enter the synchronization zone. So I have already also cut that down, and also got the information of how many pulses does it take from this moment until it completed a full revolution. So I have also got those information down. The real problem right now is the movement in which I'm trying to find the answer to. So I got the speed of this thing. I got the information on when the marker enter the operation zone. Okay, I got those information, but the trouble I'm facing now is how to and how to match up the movement of this thing. So one of the plans is to just wait for it wait for this marker to enter the zone, assuming the servo is in this position. Based on the speed information based off the encoder, the servo will start to move in that same speed, like that. But I think there's a problem with that logic, since this thing is going to do with constant bits, so I don't have to worry about that. The problem is with acceleration. The moment this thing hit the marker, it is still going at let's say 20, let's just say like x bit, okay. So it is still going at x bit and the marker, we have to accelerate to that x bit, and that is actually a problem for me. How much should we accelerate? Because we don't have any feedback until we reach the end. The end is actually not a tool to help us. It is actually a sort of marker that I use to benchmark the system on how well it is syncing. Because looking at this, if it is missing by millimeter or something, it is pretty hard to tell. So we need, in this model, I need something to benchmark that. Okay, so it's moving in this. So after doing this, how much time should I give it for it to synchronize? That is a problem. And it will definitely go on that same speed without, I don't think it will have any further information. Like I do, based on this encoder and the marker, I can derive the absolute position of these two markers. This one also have the absolute encoder based on the back of the servo. So what I'm doing is, should I base it on the velocity information or base it off the absolute position of the marker on where it is existing, and try to match the servo position based on that using some conversion. So like, let's say if the marker is here, we also know the absolute position of the marker based on the distance it has traveled from the home sensor, and we try to match the sensor with it. So like if it's in this particular position, it will translate to that particular position on the servo, and the servo will have to compensate for that. If it moves to the next position, servo move up to that position, so on. Like if it go backward a little bit, so forth, forward, like that. But the problem with that line of thinking is that there might be always a bit of a lag, because only when it moves out of position, then we get the new marker position for the servo to compare and move up to. So we are basically reacting to it, which is, I don't think it will produce a nice result with that. Another approach, in which I have said before, is to move the servo, based on the speed of the induction motor that we acquired from the encoder. So we got the absolute position, we got the speed, and we start to speed it up immediately. I don't know, like, how should I divide it up or something, or should I just fuck around and find out to see which works? Yeah, so it go like that. I would try to get it to move out of the way as well, instead of just stopping it here, since I want to actually know how well the system is moving. And then moving back really quick is also another half of the problem, because moving back is a pretty big problem all by itself. How fast can I be moving back, and how should I slow down? Because if you try to control it at maximum speed it will oftentimes overshoot it a little bit before like snapping it back. So yeah, I'm I'm a bit stuck about it, but I have made some good progress with the system for now. I also 3D printed some part over there. So I didn't play. I'm sorry, I'm having some health problem. Yeah, so this is basically my I/O allocation table, which goes where, which output goes where. Blockchain has been perfect for it. I will write the documentation at the end of this project in order to not wasting my time rewriting stuff when the main process is not done. So yeah, the best part is that I can control the variable frequency drive without needing complicated like networking from more expensive lineups controller. Basically, it's just using a pulse output 0. I don't know if you can see that. Yeah, Y0 and Y1. Y1 is the one that is controlling the induction motor. So everything theoretically will be controlled by an HMI in which I will install on the front. Probably install some emergency stop button down there as well, but for the basic movement I think I got that one down. Yeah, so just need to document it. I don't know what, I cannot find any prior resources to set up the induction motor in the post mod. So basically just digging around in the manual helps a lot. AI is actually pretty terrible in this regard because for some reason it tried to make up information that doesn't exist when I have the ground truth right here to compare it. So yeah, not very complicated, just